Yeah, thank you very much for the introduction. Thanks also, Michał, Piotr, and all of the local organizers for putting together this workshop. I'm really excited for it. Yeah, also sorry for, I realized this was supposed to be a microwave shielding session, but uh, I decided to talk about something which is much more basic than this. So you can see from the title, the rotational van der Waals interaction. It's just the interaction between ultracold molecules without any external fields. And it feels like a topic that we should really already know everything about. So it's really a bit amazing to me that I think I actually have something new to tell you, and there are also some useful applications. Okay, so just a very brief introduction is basically a summary of the previous talks, is that we want to use these molecules to do things like quantum computing, quantum simulation, precision measurement, studying ultracold chemistry. And all of these applications would benefit from very dense and cold gases. And one of the obstacles in obtaining this is the fact that molecules undergo loss in collisions. Sort of schematic of this loss process is that we think, we don't really know what happens, but we think that molecules undergo collisional loss whenever two molecules come close together. And so this is a sort of a schematic of a collision, I guess. The interaction between molecules as a function of the distance between them looks like R-6 potential, so it's an attractive interaction, and there's really not that much that stops the molecules from coming close together and undergoing some sort of loss process. So again, in the last two talks, we've seen a lot of work on shielding, where we're trying to apply some external fields, could be microwave, but also static electric fields, and there are some other proposals that create repulsive interactions between the molecules and prevent them from coming close together. So with this talk, again, I want to just take a little bit of a step back and talk about what happens when we don't do any of that and we don't apply any external fields. Okay, so this is talking about dipolar molecules, which are, well, in the simplest case, diatomic molecules consisting of two different atoms that have, and this molecule has a dipole moment along the molecular axis. Now I put dipolar in quotes because if we put a molecule without any external fields, it's in a pure rotational state with some rotational quantum numbers, angular momentum quantum numbers, Jm, then actually this molecule doesn't have a dipole moment in the lab frame. And if we take two of these molecules, then they also don't have a dipole-dipole interaction without any external fields and any first order. So what is the dominant interaction between these molecules? Is still dipole-dipole, but then in second order. So dipole-dipole goes like R-3. In second order, you get an R-6 interaction. So we call this van der Waals type interaction. And so this just comes from dipole-dipole interaction in second order perturbation theory. So I just put the expression here is grayed out, so that you don't need to be offended. I expect you know this. The interaction in some state 0 you can write as a sum over all other states of the pair of molecules, and you get a fraction where the numerator is the square of the coupling between the states, and the denominator is the energy difference. So the idea is that excited states with a small energy difference can completely dominate this interaction. So if you plug in typical numbers of for basically the dipole moment to the fourth divided by some typical energy difference, then for electronically excited states, you get C6 coefficients of 1,000 to 10,000 atomic units, which is much smaller than what you get for coupling to rotationally excited states, simply because these are spaced by much smaller energy difference. In that case, you get dipole to the fourth divided by rotational constant is about 1 million atomic units. These are very typical numbers. They don't apply to every molecule, so KRB is a notable exception. But for very many molecules, this rotational interaction is by far dominant. And so this is what I want to talk about. The other point about this energy denominator, of course, is that it's the one thing with a sign in this expression. So it determines the sign of the van der Waals interaction. If you're coupling predominantly to excited states, you have an attractive interaction, and if you're coupling predominantly to a lower lying state, you have a repulsive interaction. Okay, so the idea is just to see what this looks like for molecules in different rotational states. So this is a ladder of rotational states, 0, 1, 2, 3, and it's not equally spaced. It's spaced as j times j plus 1. So it's all super textbook. So we have two of these molecules that both have a rotational ladder, and dipole-dipole interaction couples to pair the molecules in pairs of states with this selection rule. So the rotational quantum number needs to change up or down by 1 quantum. So we start with two molecules in the rotational ground state. The coupling is to both molecules in j equals 1, and so we're coupling to an excited state that gives a attractive von der Waals type potential, and again, and so this is again very strong, very large coefficient. Okay, so then we can see what happens in different rotational states. What happens if we put both molecules in j equals 1 is that we suddenly have a couple more options. So we can couple to both molecules to be excited by one more quantum. We can de-excite both molecules, which already has a smaller energy difference. But actually, the smallest one you get by exciting one molecule and then de-exciting the other. Now, because the energy levels are spaced like j times j plus 1, this excitation energy is larger than this de-excitation energy. So again, you're coupling to a higher lying state, you get attractive interactions. Okay, so and this will be true also if we place both molecules in j equals 2 or both in j equals 3. So the next question is what happens if we put them in different rotational states? So first thing to try is put one in j equals 0, the next in j equals 1. Again, we can excite both and you get an attractive von der Waals type interaction. But in fact, there is now the other option is to excite the j equals 0 molecule to j equals 1 and de-excite j equals 1 down. So that actually doesn't change the energy. So this will give you an interaction not in second order, but in first order. You just get resonant dipole-dipole interactions. Okay, so this is well known. So people use this to access dipole-dipole interactions between molecules. Okay, so let's continue this. Let's put the second molecule not in j equals 1, but in j equals 2. Now, in this case, it looks very similar. So we have the option of exciting both, which has a large energy denominator, or we can excite the j equals 0 molecule and de-excite j equals 2, which has a smaller energy difference. So this is dominant. But now we're de-exciting like a highly excited molecule. So the de-excitation energy is actually larger than the excitation energy of j equals 0. So we're coupling to a lower lying state, and you get a repulsive R-6 interaction. So this is what I think is a bit new, and or at least I haven't seen this anywhere in the literature. This is of course super basic. But it's actually sort of the general case. This happens for essentially any combination of rotational states as long as they differ by more than 2 quanta. Also, if we put them in j equals 1 and 3, for example, you have all sorts of options, but the smallest energy difference you get by de-exciting the highly excited molecule, exciting the molecule in the lower rotational state, which gives you a state that's lower in energy, gives you a repulsive R-6 interaction. So we've already heard 2 talks about creating repulsive interactions, and so this should be useful somehow. Okay, so again, this is sort of the general case. This is a sort of schematic of this. Is this the color-coded C6 coefficient as a function of the 2 rotational quantum numbers? You see almost the entire graph is red. So the repulsive von der Waals, rotational von der Waals interaction is sort of the rule. And the only 2 exceptions are the cases that we've been looking at, namely putting both molecules in the same rotational state gives you an attractive von der Waals interaction. And 1 quantum of difference I've whited out because in fact here you get first order interactions. So I guess the point of the main message of this talk is that it's not just interesting to make one quantum of difference to access dipole-dipole interactions, but maybe also try to quanta and create repulsive from the Waals interaction. Yeah, okay, so this is to make this a little bit more concrete for a real molecule. So this is for a potential curve for rubidium cesium molecules in J equals 0 and J equals 2. As I'm showing only one curve, so it's not super confusing, but it's from like a multi-channel calculation. And you see you do get a repulsive potential. It's not completely repulsive. You get a potential barrier. So what happens is on the outside you have this looks like a centrifugal barrier, but it's the S-wave potential. On the outside you have this repulsive R-6 interaction, and then what determines the interaction here, which becomes attractive, is no longer dipole-dipole in second order, but it's really that dipole-dipole become dominant, and for the low potential curves, your dipoles just sort of interlock and interact head to tail, and this becomes attractive. So exactly what this potential looks like depends on the dipole moment and rotational constant of the molecule. Okay, so then, of course, in many of the applications, we actually do want to use the dipole-dipole interaction. So we don't get that for free by putting a molecule in J equals 2. But of course, it's kind of the same situation as you would have if you put both molecules in the ground state. You actually need to polarize the molecules to induce the dipole moment. So you can apply an electric field. And so the point is that this will change the energy levels of the rotational state. So on the left, I'm showing the lowest few rotational energy levels, and on the right-hand side, the dipole moment, both as a function of the field. So it's basically the derivative of this one. So the point is that if we apply a large field, of course, you get dipole-dipole interactions. Also, just the energy level structure changes. So this whole discussion that we just had about the J times J plus 1 spacing, this starts to break down at some point, and you can do things like this resonant shielding. But the idea is that for small enough fields below a kilovolt per centimeter or so, we're not really changing the energy level structure too much, so you do get to induce some fraction of the limiting dipole moment. So you can still use this. Okay, cool. So I think, okay, so sorry. So this is just to show that this actually works. So this is the computed loss rate coefficient as a function of the electric field. And so this is showing this again for rubidium cesium in J equals 0 and another molecule in J equals 2. The different colored lines are the different substates of J equals 2. So you can see that at low fields where this story should apply, the loss rates are suppressed with respect to this universal loss rate by 2 or so orders of magnitude. And then, yeah, if you go closer to a kilovolt per centimeter, the losses increase, but you still have some suppression, and you can induce a bit of a dipole and actually use it. So I think that's very nice for a number of applications. I just like to sketch a few. So maybe the most obvious one is quantum simulation with molecules in optical lattices. So the idea here is, again, that you can induce dipole-dipole interactions, but by doing that in J equals 0 plus 2 rather than, let's say, 0 and 1, you have the advantage that if your model actually or your lattice actually allows tunneling between sites, then you know, if that happens between molecules in the two different rotational states, that we get a suppression, like repulsive interactions, and we can actually suppress losses that would occur when that happens, when two molecules are on a single site. Now, this would be most interesting probably for fermionic molecules, because then molecules can get to a single site only if they are actually in the opposite states. And of course, for two molecules in J equals 0 or two in J equals 2, we're not suppressing collision loss. The other thing would be to study impurity physics. So if you can imagine a bath of J equals 0 molecules, you create a couple of J equals 2 molecules that can now interact with that bath without any losses. And maybe a nice thing is that then you can actually induce dipole-dipole if you induce the dipole-dipole interaction not by a static field, as I've just sort of sketched, but by microwave dressing, you can actually induce it selectively between the impurity and bath, well, also between the impurities, but not among the bath molecules. So you can sort of look at a kind of dipolar impurity, but without having a dipolar collapse of the whole gas. Then in the last part, I will be on time, but I will sketch one application in slightly more detail, not quantitatively, but because it's maybe a little bit less obvious, is the idea of using this for deterministic loading of optical tweezers with molecules. So let's also try and sort of give a bit of an introduction to what the problem here is. Maybe other people will talk about tweezers later in this meeting. But the idea is that we want to use single molecules loaded into optical tweezers, so which are just very small dipole traps that will contain a single molecule. And we want to use, you may want to use this as a platform for quantum computing. Now, if you want to do that, you of course actually need to do this loading. And this is typically done by just overlapping your tweezer with a gas of molecules that you can laser cool, so that you can actually dissipate energy and trap these molecules in this conservative trapping potential. So if you do that, then of course you try to load, and then you look at the fluorescence from these molecules to see if there's molecules in your tweezer. So you can know that there is a molecule, but then the question is, how do I know that there's only one and not two or three? So this is done by operating in what is called a collisionally blockaded regime, where you have fast collisions in the tweezer, where the density of atoms or molecules is very high. Now, for atoms, you wouldn't normally have collisional losses at all, or very slow ones, but if you're cooling, that's different because you get these light-assisted collisions. For molecules, we have collisional losses anyway, so maybe it's not very important to point this out. But the idea is that these collisional processes can remove molecules in pairs. So this means that if you load, let's say, 3 atoms here, you're left with exactly 1, or any odd number. And if you load any even number of atoms or molecules, you're left with none. So this means that you try to load your tweezers, and for half of them it will be successful. You will have a single molecule, and half of them will be empty. The nice thing is you know that it's never more than one. So the idea is that this is, is completely workable, because it means that you, after loading, you have this large but half-filled array, and this can, because the tweezers are movable, can be rearranged into a smaller but completely filled defect-free array, and you can use, let's say, as a quantum computer. So the idea of the deterministic loading would be that you sort of eliminate this 50-50 loading of single atoms or molecules, and you want to do this with 100%, let's say, maybe 90-something, but with very high probability. So for atoms, you can sort of do this because the only collisional process is this light-assisted collisions that I mentioned briefly. And so the idea is that by just changing the detuning, maybe simplifying a little bit, that you can go to a regime where this process imparts some energy into the atoms, where a lot of collisions will just impart a little bit of energy, which is fine because you laser cool the atoms continuously, so they go back to the bottom of the tweezer, and then a next collision happens, and it might happen that the energy distributes in such a way that you lose one of the atoms from the tweezer, but never two. In this case, you will basically lose single atoms, and you're always left with a single one. So for atoms, again, you can do by controlling the light-assisted collisions, and we've been working, I guess, for a year or so on a project together with Mike Tarbett on the thinking of whether you can do the same for molecules, simply by controlling light-assisted collisions, or perhaps even do something more complicated and use microwaves to protect the molecules. Yeah, I don't know if it's really impossible, but it just seems very, very hard. And the problem is that you're continuously competing with the just the normal universal loss that also leads to loss of pairs of molecules. So for atoms, you can do this stuff with like 90% probability, but for molecules, it's not so clear that you can do the analogous thing. So how does the repulsive C6 relate to any of this? So our sort of proposal, I'm not going into quantitative detail, but our proposal is to do the following thing. So we have the sequence where we're loading tweezers in this, like what I call regular, it's in quotes because there are some special requirements, but the idea is basically in this collisionally blockaded regime, we're loading single, let's say, calcium fluoride molecules for some period. And then we apply 2 microwave pulses and we repeat the whole process a number of times. So what this does is we load a number of molecules in J equals 1. That's how the laser cooling works. And not J equals 0, but 1. And this is in a collisionally blockaded regime. So we load, let's say, 4 molecules, which are then lost to collisions, and we have an empty tweezer, and this would normally be sort of game over for this. With these past collisional losses, again, because we have normal universal loss for 2 molecules in J equals 1, which has an attractive R-6 interaction. And also on top of this, there are these light-assisted collisions, which are sort of sketched by the potential in red. So the idea is that these microwave pulses, I didn't talk about it much, but they will be resonant for molecules only including the shift of their energy levels due to the tweezer. So we're not actually affecting the gas that we're trying to load from, and we can just repeat this process. So maybe the second time around we're lucky and we load an odd number of molecules, so we're left with 1 J equals 1 molecule. We apply these 2 microwave pulses to transfer the molecules to J equals 2 and then J equals 3. Then the recipe is just to repeat this again. Let's say we're doing it more than two times. So we continue with this J equals 3 molecule just hanging around. Now this is completely fine because we load more J equals 1 molecules, but the J equals 3 molecule doesn't undergo collisional loss with these because the normal von der Waals type interaction is now repulsive, and also there are no light-assisted collisions because the dipole moment from our excited state is to J equals 1 only. This is how the laser cooling works. Okay, so then this looks like a problem. We then apply these 2 microwave pulses, which transfer the molecule from J equals 2 to J equals 3. So now it would seem that we no longer know that we've loaded a single molecule if there is one. So the way that this is fixed is by a dipolar blockade. So the idea is that the J equals 3 molecule, if it has been loaded previously, will have resonant dipole-dipole interactions with J equals 2, which will shift its energy levels. And so the second microwave, or the first microwave pulse is actually no longer resonant, and it will not transfer the molecules. So this is repeated a couple of times, and you get rid of maybe the J equals 1 molecules, and you've loaded J equals 3 molecules in all of your tweezers with very high probability. So this is so this is not really quantitative, but we're still working out some of the quantitative details, but we think that we can definitely get an improvement over this 50% loading. Okay, so I'm still on time, so let me just conclude. So I've discussed this rotational von der Waals interaction, and the main message is that it's repulsive for molecules in most combinations of rotational states, as long as they differ by more than 1 quantum. And so this can be very, very nice for many applications. I've discussed a few, so quantum simulation with molecules in optical lattices, studying impurity physics, and also deterministic loading of optical tweezers. And maybe there are more applications that we haven't really thought about yet. So I'd like to thank Etienne, who's the PhD student on the project, and Mike, there's no picture, but he's in the back, for teaching us about the laser cooling and tweezer loading. And thank you all for your attention.
thank you, Tijs, for perfect timing. Now I also learned how to use this timer. Okay, so questions? Yes, Giovanni?
So, Tijs, you showed us that the strength of the rotational dispersion dies off as the difference between the rotational number increases, and presumably it also dies off as you get higher rotation states. But you also mentioned that the turnover in it and the short range attraction that eventually kills it comes from excited rotational states. Does that mean that in fact the height of the barrier doesn't die off too badly? So if you've got two fairly high rotor states, they actually, even though the dispersion is weak, does it carry on going up for longer so you get decent height of barriers?
Yeah, I'm not sure. I'm not sure if okay, so if we're looking, oops, oh no, sorry. So we're talking about this one.
Yeah.
So yeah, if you make, if you go away further from the diagonal, then it dies off quite quickly. I think along the diagonal it's less bad.
Yeah, but it's your next slide that I was mostly thinking of, because you've got this turnover. Yeah. And if the place where the turnover happens gets closer in, because you've got a bigger excavation range of the higher ones, then it might be that the barrier doesn't go down. The barrier doesn't go down as fast as the repulsion with positive coefficient.
Yeah, I'm not 100% sure, but there's definitely a dependence, and also like the point where it happens, right? Because that's probably like the width is probably more important than the actual height, and it does depend quite a bit on the system also. So here we have it for rubidium cesium, we have a barrier height of let's say 100 microkelvin. I think I have one slide. For sodium potassium, it's almost 300, so there's quite a bit of dependence on this also, which is because these two effects depend on the dipole and rotational constant both, like the repulsion and this bit, but they depend on it in different ways. So yeah. Okay, Leszek?
When you have this molecule in one of them in J equals 0 state and the other in J equal 2, it's like having two hydrogen atoms, one in the S state and another in D state. And then the dominant term for large distances will be, you will have resonant quadruple interactions in the first order, which will go as 1 over R to the 5th. And then it will dominate 1 over R to the 6th.
Yes. Yeah, I think that's right. That must be dominant at some very large distance. I'm not sure if it affects this barrier too much, but yeah, it's a good point. At very large distances, this will be dominant.
Well, let's always go to higher J's for that, and then the argument can go away.
Right. Yeah, no, it's a good point. Thank you.
Okay. More questions? Let's do 1 minute. Okay, if not, then probably we want more coffee.
Yes.
So we now go for a break, but because we have some delays, so we will start 10 past for the next session after the regular. So once more, thank you, Tijs, and other speakers for this excellent session.